Now that we've explored the fundamental concepts of a knowledge graph, let's look at how they're put into practice. In this lesson, you'll use the Cypher query language to interact with a fun knowledge graph that contains data about actors and movies. Let's dive in. Okay, to get this notebook started, we're going to import some packages that we need for just getting everything set up for being able to access Neo4j and getting the environment. Those are classic packages we're going to get from the OS and from, of course, everybody's friend .env. Also, we're going to be loading from LangChain the Neo4j graph class itself, which is how we're going to be accessing Neo4j. So with those packages imported, we're then going to set up Neo4j itself by getting some environment variables. And of course, loading from .env and then setting up some variables here. Now, the variables that we're setting are all, of course, named Neo4j. This very first one, the Neo4j URI, is basically the connection string for where is Neo4j located, at what port, those typical kinds of things. We, of course, need a username and a password, and we're going to specify which database within the DBMS we're going to be using. And so let's run that as well. Okay, now that we have our environment set up, we're going to create an instance of this Neo4j graph class. That's basically going to be a driver or a connection to the database that we can use from within Python. And because we're building a knowledge graph today, we'll call the Neo4j graph instance KG, short for knowledge graph, of course, using those environment variables we just set up. Okay, now the notebook is ready to start sending Cypher queries against this knowledge graph. But what is the knowledge graph that we're actually going to be using? Well, let's take a look at that first. We know that it's got movies and it's got people. So here's an illustration of what that looks like. On the left here, we've got some person nodes. We know that they acted in some movies, right? So the actor becomes an actor because they've acted in something. If you can read that out as a sentence, of course, it's that a person acted in a movie. So that's the fundamental pattern that we'll be looking for when we're dealing with this data set. For both of those nodes, for the persons and the movies, we know that they have properties, the properties that are available for the person, or that they all have names. And they also have a born value, which is just the year that they were born as an integer. The movies have a title and tagline, both as strings, and they also have a release date, also just an integer about the year the movie was released. And finally, just in the same way that I mentioned that a person acted in a movie, there's more relationships that a person might have with a movie. So here's all the different relationships between a person and a movie. We know that they've acted in a movie. A person might also have directed that movie. Sometimes for some movies, we know that a person both acted in and directed a movie. Also, they might have written a movie, so that there's a person might have wrote that movie, a person might have produced that movie, and finally, somebody might have reviewed that movie. That's all the different relationships between the persons and the movies within this data set. But then the persons themselves have a relationship with other persons. Here it's the idea that if somebody has reviewed a movie, somebody else might be a follower of that reviewer. And so these are all the relationships that are present. And what's interesting about this aspect is that all we've had to say is that these nodes that are persons are persons. What those persons' roles are, the relationships around them to the movies and to each other persons is what really determines the type of a person that they are, or the job that they have, or their behaviors within the data set. It's worth observing, of course, that these are potential relationships. The actual relationships themselves for particular people on particular movies ends up being dynamic based on the data itself. So now we have some idea about what the graph looks like. We know that we have people, we know that we have movies, and the relationships between those people and those movies. Let's start doing some querying in the Python notebook. Now the querying that we're going to be doing is based on Cypher. Cypher is Neo4j's query language. It is using pattern matching to find things inside of the graph. And it looks like this. Here I'm going to take a multi-line string in Python and assign that string to this variable Cypher. The Cypher itself begins with this match clause. Match is pattern matching, and the very smallest pattern match you can look for is a single node pattern. Here I'm going to assign the results of that pattern to a variable I'm calling n, and then in this next line, I'm going to say return a count of how many of those n's you have found. So if the result of running this query should be how many nodes we have in this graph, whether those nodes are people, whether they're movies, or something else, all the nodes should be counted in this query right here. So go ahead and assign that variable. To run the query itself, we're going to take advantage of the LangChain integration we set up before, and we've got the kg.query function that's actually going to take the Cypher that we defined above, run that Cypher, and return a result, and then it will just show what the result actually looks like. So you can see that the result is actually a list of rows, basically, that come back from the query of Neo4j. And in that query, each of the rows is then a dictionary, where the dictionary keys are based on what you've returned from the return clause up here in the Cypher. So here we've been returning count n. So we got a key for count n, and the value of that is 171. So there's 171 nodes within this graph. Now count n as a variable name or as a kind of key within this dictionary isn't the greatest. So there's also the option of actually renaming those things using an alias. So we can say count n as, let's call it number of nodes. That's a little bit friendlier, right? So we'll redefine that cipher, and then we'll rerun the query itself. And now this looks much nicer. We have number of nodes, obviously the same result, it's still 171. Cool. Now that we know that we're getting that back, instead of looking at the raw result, we can take advantage of some nice print statements in here. And I can run this as well. Okay, so with that cipher match that we just did, we looked for a pattern of all of the nodes within the graph, returned a count of that. What if we don't want to find all the nodes in the graph, but just the movies or just the persons? The movies and the persons show up as labels on nodes. So all we need to do is modify that match we had before and add a label for, let's say, movie. So let's go ahead and do that. We'll start with the same cipher query we had earlier. And this small change we have to make is instead of this n being all by itself, we're going to add a colon, and then we're going to say movie. Movie is the name of the label for all the nodes that are movies. We're going to return a count, and instead of number of nodes, we'll just say it's the number of movies. Running that then, of course, shows us the number of movies are 38 within this data set. Pretty good, just enough for us to play with. Okay, that's great. It got the result we expected, and that's really nice. There's one more small change we can make here to this query to improve the readability of the query. We've been using this variable n to capture all of the patterns that match these nodes, but we know that we're grabbing movies, and movies begin with the letter M instead of N, so let's go ahead and change that. We can use M:movie, and then return a count of those M's, and running this again gets us the same result. All we've done is change the name of the variable to help readability of the query. You have a count of all the movies in the graph. We can do the same thing with people as well. We can just modify the query we have here. Instead of matching for nodes with the label movie, we'll change that to person. And we'll change the name here as well. We'll say this is people. So we're going to match a pattern for people with the label person, so nodes that have the label person. We're again going to do a count of those nodes, and we'll rename the result to number of people. And let's run that. Cool, perfect. So now for any set of nodes within the graph, you know how you can match just those nodes and then get a count of them. It's a nice place to start for exploring a new graph. When you're exploring the graph, you can, of course, add more match criteria. For instance, looking for a very specific value. Value-based criteria are introduced with a kind of object notation inside of curly braces, then the name of a property and the exact match to look against. So for example, if we want to find not just all people, but a very specific person, we'll just make a copy of this and modify it. So instead of just, all people with the label person, let's look for Tom Hanks. So we'll say we'll do match for Tom, who's a person, and we'll introduce the curly braces here, where we want the name of this person to be Tom Hanks. And we don't need a count of Tom Hanks. Let's just go ahead and return Tom himself. So we're going to do a match for Tom, who's a person with the name Tom Hanks, and let's just return Tom. So running that query, we then have a list of results where there's only one result, because in this movie data set, there aren't other people named Tom Hanks. So we found Tom Hanks. We can see when he was born, and that's all the properties we have on this particular node. You can, of course, do the same thing if you happen to know that there's a movie that you're looking for. So let's copy all of this over, and we'll change it. Instead of looking for a person, we're going to look for a movie. And I think the movie that should be here is an oldie but a goodie called Cloud Atlas. And it's not a name, but that has a title of Cloud Atlas. And then we'll return that movie node. So there's Cloud Atlas. We can see that it has a tagline. Everything is connected. It's why it's so close to my heart, of course. The title is Cloud Atlas, and it was released way back in 2012. For these last couple of queries, we've been looking for specific nodes, maybe based on some exact match criteria. If we didn't want to return the entire node of Cloud Atlas and just, let's say, the release date, we can return just that. Let's make a copy of this query and just modify the return clause. So here, Cloud Atlas will be, all of the nodes that have this title Cloud Atlas. We know that they have a title and they also have a release date. So we're going to add release there and then run that. And now the values that come back are just the release number itself, not all the other properties. You can, of course, return multiple values back if you'd like to. So we'll make one more modification to this, and we'll return two things. In addition to the release date, we will return the tagline, let's say. So Cloud Atlas tagline. And now we get a dictionary back in this list that has just those two fields that we were interested in. For the patterns we've been describing so far, we have been having exact matches for nodes that have particular labels, and then we did exact matches for particular values within those nodes. But if you didn't know the exact value that you're looking for, you can also do range type queries. So you can do conditional matching within the property matching. So let's take a look at that. Let's say you want to do, for these movies, this is kind of a classic set of movies we've got here. Let's find all the movies that are back from the 90s. In code, the Cypher query looks like this. The first part is exactly what we've done before. We have a match clause here with just a single node pattern. And now we're going to use a where clause to qualify that pattern match that we're doing. So 90s is going to have all of the movies, so anything that's got a movie label. And then the where clause will have a conditional matching for like what properties within that we actually care about. So here we'll do a range value comparison both on the release date that is bigger than 1990 but before 2000. So all of the movies from the 90s. For those movies, we'll return just the titles to see what those movies are. So that's the query. We'll get that set. And as before, we'll use our LangChain integration for running this against the database. And here they are. All of these classic great movies from the 90s. Okay, there's a lot more we can do with just single node patterns themselves, but let's get into some more graphy things by introducing relationships. We know we have people who acted in movies. So let's take a look at some examples of like who the names of the actors are and the movies that they've acted in. We'll do that with a slightly bigger pattern. The Cypher query itself starts off very similar to what we had before. We're going to match clause. It's going to match some actors who we know have the label person. And now here's the fun part of the relationships that we're introducing. Here it's an acted in relationship with some movies that we don't know about, but we know that those have the label movie on those nodes. For the patterns that are matched inside of the database that have those actors and those movies, we're just going to return the actor name and the movie title, and we'll limit the results to just 10. So kg.query and or Cypher. Right. Cool. So now we have a bunch of actors' names and the movies they've been in. Of course, this is very matrix heavy because we love the matrix at Neo4j. And you probably recognize some of these names, but maybe not this first name. I'm not sure that's quite right. Let's come back to that later. If there's a particular actor we care about and finding out what movies they've had, we can do that as well using some of the conditional matching that we looked at before. So let's say we remember that there's, of course, Tom Hanks in this data set. So let's take a look at a Cypher query that introduces him back into the mix. So here's what the Cypher looks like. We've got a match clause. We're going to say there's a person whose name is Tom Hanks and that he acted in some Tom Hanks movies. Let's return that person's name, tom.name, and also the Tom Hanks movies.titles. So fantastic. Now we see that we've got Tom Hanks and all the movies that he's been in that are in this database. So while we're dealing with Tom Hanks, it might be interesting to extend this pattern a little bit even further. The pattern that we have right now is from a person who acted in a movie. We can think about, well, who else acted in that movie? So the pattern now would be from a person who acted in a movie to some other people that acted in the movie. This gets really interesting now. Let's take a look at what that query looks like. So in Cypher, this ends up being a little bit long, but we can read through it here together. So the match clause is now match a Tom who's a person where the name is Tom Hanks. Tom acted in some movies, we're just going to call M. And here we're not even going to use the label for the movies. We know that the person who acted in something is going to end up in some movies. And then coming in from the other direction, we also have a new relationship, also acted in, and that's going to be assigned to some nodes that are co-actors. So on this right-hand side, we've got, still we know there are going to be people who acted in the movies. What we really care about are those co-actors at the end. And then we're going to return the co-actors, their name, and the title of the movies that they co-acted in with Tom Hanks. And as before, kg.query to run this bit of Cypher. Cool. So here's all the people that have acted with Tom Hanks in various movies. It's a long list of people. Maybe not quite Kevin Bacon long, but quite long. You may recall that earlier we noticed an actor named Emil Ephraim in the Matrix movie. Emil is not an actor in the Matrix. He's actually the founder of Neo4j. We can leave him in the knowledge graph because he is a person, but let's remove his claims to acting fame. So before we do that, let's first find what other claims Emil might have made. By doing similar to the query we did with Tom Hanks, we're going to match against a pattern where we have Emil, who's a person whose name is Emil Ephraim, and he acted in some movies. Let's return Emil's name and the title of those movies. Okay, so he only has that one claim for being in the Matrix. Now we'll go ahead and do a very similar query, but instead of just returning some results, we'll remove that acted in relationship. You can take the query we just had, because the matching is perfect, but instead of returning some data, we're going to use a new clause called delete. And delete will delete whatever we want to from the database. Here we want to delete these acted in relationships, so we'll say delete acted in. Cool. We didn't return any results from this query, so the result set itself is actually empty. Let's verify that Emil is now gone and is no longer an actor in the movie, The Matrix, by running this previous query again. Okay, now we get no results even for that match, because of course the match fails to find anything within the data set that satisfies the pattern of this person whose name is Emil that acted in some movies. Exactly what we want to see. Okay, let's take a look at creating data. Creating data is very similar to doing matching on single nodes. Let's take a look at, for instance, creating a new person. I'll create just myself. If Emil is going to be in this knowledge graph, I can be there too. So the Cypher query looks like this. Instead of a match clause, we're now going to have a create clause. We're going to create an Andreas. We're going to give it a label person, and we're going to give Andreas a name property where the value is Andreas. And then we'll return the node we just created. And just like that, I'm part of the knowledge graph too. We also want to be able to create relationships. We can take this one more step. Okay, now that we have me inside of the knowledge graph and we have Emil inside of the knowledge graph, let's add a relationship between me, Andreas, and Emil. Adding relationships is a little bit different than adding nodes because the relationships contain two nodes. So the first step is to have a Cypher query where you're going to find the nodes you want to create a relationship between. So this pattern is a little bit different than we had before, and let's take a look at it more closely. We're going to match an Andreas who has a labeled person and a name Andreas, and then we're going to use a comma instead of a relationship here because a relationship doesn't exist yet. We're also then going to find an Emil who also is labeled with a person where the name is Emil Ephraim. Having found those two nodes, we'll then merge a new relationship in. Merge is very similar to the create, except that if the relationship already exists, it won't be created again. So merge actually combines a match with a create clause and does the right thing depending on whether or not the data exists. So we'll merge Andreas, say that he has a relationship where the type of the relationship is works with and works with Emil. Let's return that Andreas, the relationship, and Emil. Great. So we can see there's the Andreas node, there's the relationship, has a relationship where it's a works with relationship type, and then the Emil Ephraim node as well. Emil happens to have a few more properties that we didn't add to Andreas, but that's totally cool inside of the knowledge graph. So in this lesson, you learned the fundamentals of querying a knowledge graph using the Cypher language. You're working towards building a RAG application, and this requires text embeddings of some sort. In the next lesson, you'll see how to transform any text fields in your graph into vector embeddings and add those to the graph to enable vector similarity search. Let's move on to the next video to get started.